and I assigned you guys a little bit of homework. Obviously, the homework's not due today. Remember, the homework is always due Sunday at midnight at the homework check, so any homework from that week wouldn't be due at the earliest Sunday at midnight. But I'd like to take a few minutes here at the start of class and field any questions. If anybody has any questions about things that you've seen from the homework, that's fine if you don't. But like, that's the idea with the homework check being Sunday at midnight. Gives you a chance to come in and ask questions about stuff, and we can clean that stuff up before anything has to be due. Mackenzie, number 9. Sure. Just grab that. All right. So, okay. So we have f of x is equal to the square root of x minus 1. Again, since this is kind of contextless, you know, there's no story problem associated with it. I know the implicit domain is just going to be all real numbers. For the relevant domain, I'm going to look at the operations involved in this function. So I see 2 operations. I see subtraction and I see a square root. I know that the subtraction of 2 real numbers is no big deal. That doesn't cause any problems anywhere. But I know that if I take the square root of something, that has to be a non-negative number. So I'll take everything that's under the square root and set it greater than or equal to 0. And then I can solve that inequality just by adding 1 to both sides. And then I'll write my interval notation. The lower bound here for x is greater than or equal to 1 is 1, and the upper bound is positive infinity. We know the infinities always get a parenthesis, and because it's 1 is greater than or equal to 1, we should have a bracket on the 1. So there is my relevant domain. Does that feel okay, Mackenzie? Okay. Anybody else? Okay, no problem. You can always follow up again next time. Not a big deal, but if you guys got it, I'm good. Today, we're going to start with section 4, talking about increasing and decreasing functions. So I'm just going to start with a couple of definitions. So we say that a function f is increasing on a given interval if for any 2 points on that interval a positive change in x results in a positive change in f of x. And we'll do some visual examples here in a moment to kind of really hammer this point home and get a little bit better picture of what this definition is really saying. Oh my goodness, sorry. We have two more definitions real quick that are almost the identical wording, so I'm going to just do a little bit of copying and pasting and editing. So we say a function is decreasing on a given interval if for any 2 points on that interval a positive change in x results in a negative change in f of x. And we say that that function is constant on the given interval, yada, 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 results in no change in f of x. And I'll pause here if you're copying everything to give you a chance to get caught up there. If I were you as a student, I would have just written the definition and done like above increasing would have done decreasing, and then negative, and then above that it would have constant and no. So I wouldn't have to copy it a bunch of times, because if you're writing things down by hand, you can't copy it, you know, cut and paste like you can in OneNote. You know what I mean? But whatever you guys want to do is cool. If you're doing it in OneNote, obviously you can do what I did, just copy and paste and like edit a couple of words, and you know, it's no big deal. I'd imagine that by the end of the day your hand can be tired, especially the first couple of weeks back of school when you're not used to writing a lot, unless you were writing a lot during the summer, but I kind of doubt it. I know I didn't as a high school student. Okay. So let's look a little bit at an example here, and we'll talk about how these definitions relate to the example. And then I'll give you like a little bit of a more intuitive way of thinking about a problem or about these definitions. So let's say we have some function that looks like this. Kind of the more intuitive way about, or thinking about increasing, decreasing, and constant is imagine you got like a little person that walks along the graph as you move from left to right. On this first section of the graph, our little person is walking uphill. That means the function is increasing. The next section of our graph, our little person is on the flat section. That's a constant part of the function. And on the last section, our little person is walking downhill. That is the decreasing section. The thing you need to make sure that you're remembering is that our little person is always walking from left to right. Just like how we read a book, at least in English. I think some other languages read the other direction. But all of us can read English. The way we read a mathematical graph is the same way we read from left to right. Does that feel okay there? So just to illustrate the definition here, it's saying like, okay, let's say we look at this first interval. If I take any 2 points, if I have a positive change in x, so that I'm taking the right point and subtracting the x coordinate from the left point will give me a positive change in x, correct? I should also get a positive change in y when I subtract them in the same order, because the point on the right is higher than the point on the left. So the change in y should be positive. And you can see similarly how that would translate all the way through. So that's why in the definition it's always a positive change in x, is that you're taking the right-hand point and subtracting from the left-hand point. So you're looking at moving from left to right. Okay, let's add in a couple of coordinates here so that we can maybe write our intervals of increasing and decreasing. So I'm just going to make up some points or some labels for these points that look reasonable. So our first section is this uphill section. We said that that is increasing. We're writing an interval to describe where the graph is increasing. Whenever we write these intervals of increasing, decreasing, or constant, we're always referencing x coordinates on the graph. If you're asking where is something happening on the graph, you can describe that uniquely with just the x coordinate, because you could always plug that x coordinate into the function to get the y. Is everybody okay with that? Okay. So our function begins increasing here at the far left end. Because it's capturing the left arrow, that implies that the leftmost point is negative infinity. And it stops increasing here at this point, negative 2, 3. So the upper bound for my interval of increasing is negative 2. Now we know the infinities always get a parenthesis. And based on the definition of increasing, any finite endpoint will also get a parenthesis. And that's because if I pick 2 points on the interval, I can't pick a point to the right of negative 2 and still have it increasing. So the endpoints are always going to be have parentheses in our intervals. Joe?
What does the E mean again?
That just means like it's a member of the set. Yeah, so that's like, looks like the letter E, but instead of having like hard corners, it has like curved corners, is what I'm trying to draw there. Okay. The next section of our graph is the constant section. That constant section begins here at negative 2 and ends here at 4. And again, as I just explained, for these intervals of increasing and decreasing and constant, you can't have any brackets on it because there can't be a point to the right of the endpoint, so you can't call the endpoint increasing, decreasing, or constant there, just by the way we define that. And then our last section is the decreasing one. The decreasing begins at 4. And it continues on to the right-hand arrow, so that will be positive infinity. And again, both of those will be parentheses. Everybody feel okay there? Good. I'm going to do one more example that's a little bit more complicated, just so that I get a good picture of what's going on. I'm going to generate this graph using the computer and then just copy and paste it in here so that it's a little bit easier to kind of see what's going on. And it'll be kind of good practice for, on a test or whatever, I would generate my graph in a similar fashion. So this would be like what an example problem might look like on the test, rather than seeing like my hand-drawn gobbledygook here. Actually, let's leave that big and just shrink the picture down. That's probably better. Just a little big. Yes.
Like, will not now on be like all graphs?
No, not all graphs. But these terms, mainly what we've been talking about here the last couple of days, are just like some conceptual vocabulary. So there's not a lot of computation that we're expecting from you guys to do here, but that would not be the case always. And in fact, when we get into the next chapter, that kind of returns to a little bit more computational focused anyways. Okay, so I have this graph. Just for clarity's sake, any place where we see the graph leaving the viewing window here, you can assume there's like an arrow at the end of it, that none of these like are finite. They all just kind of keep going. Everybody's okay with reading that way? I think that's probably would be what you'd assume, but I like to say it anyways, just so that we're crystal clear about things, because you get a very different answer if you assume that like they ended as soon as at whatever point they were at the end of the screen. Okay, if I take a look at this, how many intervals do you see that are increasing on this graph? How many parts of the graph do you see that are increasing? 2. So this one on the far left, if we walk from left to right, we're going uphill the whole time until the graph ends at that asymptote. Everybody good? The second interval starts here after the asymptote, and we continue walking uphill until we get to 0. Sound good? How many intervals of decreasing do we see? 2. Okay, if we continue walking from 0, we go downhill until we get the asymptote. And we start after the asymptote, we walk downhill the whole way. How about the intervals of constant? There's not any, right? Well, it has to be an interval, right? So a single point can't be an interval. So, good. Okay, so now let's write these intervals. Now, because the graph is in 2 distinct chunks, we have 2 distinct intervals, one interval that's increasing, one interval, or 2 intervals that are increasing. I know I'm going to have to use like 2 intervals with a union in the middle, so I'm going to just go ahead and write, well, I probably should write x as a member of first and then put my u in there so I have enough space to kind of cram everything in. And similarly with my decreasing, I'll do that right away. Okay, my first interval of increasing, well, starts here with the left-hand arrow. So that's going to be negative infinity. And it goes all the way into the asymptote, which looks like negative 3 when I read it off the graph. Yep. And my next interval looks like it starts here at the asymptote, so negative 3, and ends here at 0. Everybody feel comfortable with that? Okay. For the decreasing, well, it starts here at 0, and it goes all the way to the asymptote, which looks like positive 3. And then the next piece starts at the asymptote, so positive 3, and goes all the way to the right-hand arrow, which would be positive infinity. Joe?
What's the definition of an asymptote again?
So it's just one of these lines that the graph approaches but doesn't cross.
Okay.
So there's just like an imaginary barrier, like a force field or whatever. You get right up close to it, but you can't touch it or cross it. Feel good? Again, not too difficult of a concept. It's nice because it's the definition, while precise, would allow us to like prove things. Really, just the visual kind of definition that we talked about, imagining our little person walking along the graph, is good enough. And there's no computation to speak of here. It's just looking at the picture and kind of describing what you see using the proper notation. The next topic here that I want to talk about in section 4 is about extrema. So there's 2 types of extrema. There's maxima, which is the plural for the word maximum. And then there's minima. So we say that a maximum of a function f is a value f of c that is greater than or equal to all other range values of f on some interval containing c. And then we have maxima, or maximums. Really, again, maxima is the plural for the word maximum. Oh boy. What happened here? I thought I copied this. We also have minima, again, which is the plural for the word minimum. What's going on here? There we go. Which, as you might have guessed, is going to be like almost the same definition. I'm going to do my same cheat code of so again, same idea, but the minimum is less than or equal to all the other range values on that interval. Now, there are 2 types of maximums and there's 2 types of minimums. So you have absolute or global. We use those 2 terms interchangeably, maximums and minimums. So something is an absolute maximum if it's the largest range value, or tied for first largest range value over all ranges, or all values in the range, I should say. Is everybody okay with that? So that probably doesn't, the word there gives you a pretty good idea of what that is. The local is the other kind. And a local maximum is a maximum that's for just a small neighborhood. So if I don't look at the entire graph, but if I take just like a little chunk of it, it's a high point in that chunk. In general, visually what you're looking for, maxima are generally like the top of hills, and minima are generally the bottom of valleys. The one place where that might not be true is if you have a function that doesn't have arrows at both ends, because then the endpoints of that piece might also be a maxima or minima. But that's the only case where it's not a hill or valley. Everybody feel okay about what I mean by maxima, minima, global, local? We'll do a visual example here in just a moment. Yeah, global is the like of all the ranges, it's the biggest, or tied for first, or smallest, or tied for last. And then local would be just in a, not looking at the whole graph, but just like a little neighborhood. It's a high or low point.
Okay, so local would be in a graph that like probably tell you like a local.
Well, let's do an example here. Okay. So let's say we have f of x equals x to the fourth plus 2x cubed minus 4x squared minus 3x plus 1. Our calculator can actually find the locations of maxima and minima for us. So we'll do that at the same time as like looking at the picture and figuring out what's going on, okay? So if you want to follow along on your graphing calculator, you're welcome to do so. If you don't have it with you, or you're like, yo, I'm a sit and watcher, that's totally fine also. The calculator part in the video looks like it's at about the 28-minute mark. If you're like, yo, I didn't have my calculator with me and I want to follow along and do this, because if I don't do it by myself, I don't know how to do it. You can always go back and watch it. Yes? Of course. So to graph something on your calculator, start by turning it on. The on button is located in the bottom left-hand corner of the calculator. In order for our calculator to find a maximum or minimum, it has to have the graph of the function that we're looking for the maxes and mins on. So to graph something on our calculator, we'll start by pressing the y equals button. The first thing I'm going to do is make sure that all these y equals are cleared out. So I'm going to clear anything I have on there. And I'm going to continue to scroll down all the way to the bottom to make sure that there's no gobbledygook left at the end. Our calculator probably hasn't been on more than once or twice this summer, so if it was sitting around in a backpack with the cover off and buttons get kind of pushed, you can end up with goofy stuff down there at the bottom, and that can cause a problem. Once I've checked that all of my y equals slots are empty, I'm going to take a look at the top where it says plot 1, plot 2, plot 3. I do not want any of the plots highlighted. If you notice that any of your plot 1, plot 2, plot 3 are highlighted, you'll need to move your cursor up there and just press enter to unhighlight it. Okay. What I'm going to do now is I'm going to type in my function exactly as it looks on my piece of paper. So the X button is here next to the green alpha button. The exponent button is there above the division symbol. And everything else is just like a button on the home screen that is obvious as to where it is and what it is now. So once you've typed in your function into your calculator, we need to set a viewing window on which to graph this on. Again, it's probably been, like 2 or 3 months since we picked up our graphing calculator. Who knows the window that we last used to look at something? In that case, the easiest thing to do is just to do zoom and then pick option 6 for me, which is Z standard, which is just going to give us the standard viewing window from -10 to +10 on the x-axis and -10 to +10 on the y-axis. Rather than going and doing that manually, the calculator has that as a built-in default for that zoom. All right. So if I go and I look at my picture here, I see a global minimum here where my mouse pointer is. That's the lowest point on the entire graph. I have a local maximum here. That's a relative high point for the neighborhood, but not the highest point overall. I have a local minimum here. Again, that's a relative low point, but not the lowest point overall. And I have no global maximum because the arrows are pointing up. So any point that I find, I know there's another point higher than that. So I'm just going to kind of record that information. So I have a global minimum, then I have a local maximum, and then I have a local minimum, and my global maximum, there is none. Yes, Paul?
So, Rick, would it be impossible to have a global maximum in this situation because you have an arrow going up?
Correct.
Okay, so the global maximum would be the highest point regardless of either direction.
Yes.
Okay.
Yeah, it's the highest point on the graph. And if there is no highest point because you have arrows going up, then you have no global maximum.
I understand. Thank you.
Yep. Okay. Now what I'm going to do is I'm going to find the values for these points. The calculator can help me do that with a great deal of accuracy. Now it can't give me the exact value at some point. Most of these are going to be decimals and the calculator is going to like truncate the decimal, but it's like get you to the moon good enough accuracy, if not actual value. You know what I mean, guys? Okay. So to get to the menu to find these maximums and minimums, we're going to press the second button. That's the blue one. And then the trace button, which is on that top row on the fourth button there. The first thing we're looking for is the global minimum. So from these commands here, which one does it sound like I want? Minimum. So I'll go ahead and select that. The calculator is now going to ask me 3 questions. Here at the bottom, it says left bound. So what the calculator needs me to do is find a point to the left of my global minimum. So like somewhere over here would be good. It doesn't really matter where, but like somewhere on the left side of the minimum. So my cursor is right here. So I'm just going to use my left and right arrows to move my cursor to where it's on the left side. And then I'll press enter. It then asks me for right bound. So I'm going to move my cursor so it's somewhere like over here, that it's on the right-hand side of that minimum I'm looking for. That looks good. And I'll press enter. And as long as that range of values that I've picked only contain one extreme point, the guess doesn't matter. I'm just going to press enter exactly where it was again. And you'll see at the bottom of the calculator, it gives me the coordinate of that point, the x and the y. I'm not going to write down all those decimal points, but I'm going to round it to 3 decimal points, I think seems pretty fair. Everybody okay with what we did there? Next up is the local maximum. I'm going to do the same thing. So I'll press second and trace to go back into that menu. But this time, instead of picking the minimum command, I'm going to pick the maximum command. So again, the calculator is going to ask me the same 3 questions, left bound, right bound, and guess. So the left bound here should be somewhere on this part of the graph. That's on the left-hand side of that maximum. So I'll move my cursor over there. That looks good. Press enter. then needs a right bound. So I'm going to move my cursor over here. It's on the right side of that maximum. So that looks good. Press enter. And then because I have only one extreme point inside of in between my left bound and right bound, I can just press enter and not have to worry about moving the guess around. And then it gives me the coordinate for my local maximum. I'm just going to round that to 3 decimal places. And then I have one local minimum left. Why don't you try to find that local minimum on your own, just if you're following along on your calculator, so you can practice doing this process real quick on your own. While you guys are doing that, I'm going to do it on my own also, but I won't say what I'm doing along the way, so hopefully not to interrupt you. And you can check what you got versus what I got, just to make sure that you did everything correctly. How'd that go? Those of you following along anyways. Did it go good? Think you got it? It's not too tough. You probably did it last year in the Algebra 2 class also. Joe?
When's our first test next week?
Oh, unlikely. We have a couple of big sections still next week, so I don't think... we may have like the review day next week, but the test will probably be the week after, would be my suspicion. But that's just, yeah, that's probably about right. Especially with a 4-day week coming next week. So probably be the week after, because we have that Friday off for the Labor Day weekend. Okay. We feel good about increasing, decreasing constant and at maxes and mins. The one nice thing here is without even looking at the graph, if I have the list of the maximums and minimums like this, I can write my intervals of increasing and decreasing, assuming that I know my graph is continuous. As a nice helpful fact, if I look at this example function, this is a polynomial. All polynomials are continuous functions. So that helps a little bit. So what I can say here is, since I know that my graph, let me do this real quick. Since I know I'm starting with my global minimum, and I know I'm starting with that because that's the x-coordinate that's the furthest to the left. It's the smallest x-coordinate. So the first thing I'm going to have is like some global minimum, right? So up to that global minimum, I am decreasing because it's heading down. Does everybody kind of see that? So that's negative infinity to the x-coordinate of my global minimum. From my global minimum, I go up to a local maximum. So in that section, we're increasing. So from the global minimum, and I look at the x-coordinate there, to the local maximum, looking at the x-coordinate there, I am increasing. Then from the local maximum, I go to a local minimum. Well, that's decreasing. So the local maximum's x-coordinate to the local minimum's x-coordinate. And then from the local minimum, there's nothing after, so it just must continue going forever in that direction. So that last section is increasing. So from the local maximum's local minimum's x-coordinate to positive infinity. That was supposed to be an infinity. Is everybody okay with that? Again, I didn't have to look at the graph specifically.
Is Evan no good here?
He is.
This is from Coach Fox.
Okay. I could just kind of look at whether they were maxes and mins and the order in which they came and kind of determine my intervals of increasing and decreasing there. Yes?
So how did you know the order?
You look at the x coordinates. The smallest x coordinate is the first one. The next smallest is the next one. You know, you just go from left to right. So again, the takeaway here is that the bounds of my intervals are going to match up with the x coordinates of my extreme points, my maximum and my minimum. Which is kind of nice, right? If I have the extreme points, I can write my intervals of increasing and decreasing without even looking at a graph, provided I know that it's continuous, right? You could also have changes of changes from increasing to decreasing at discontinuities. Also, that's possible. So keep that in mind. Okay. The next section, the last section we're going to look at today, we're going to talk about symmetry. So again, increasing and decreasing are basically describing attributes of functions. Like this function is increasing here and it's decreasing there, and you know, blah, 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 blah. Symmetry is also another descriptor for functions. So we can describe you know, a function has this symmetry or that symmetry or whatever. So we're going to look at three major types of symmetry today. There are others, but these are the major ones, and I wouldn't expect us to worry about anything that we don't talk about today. So the first type of symmetry is symmetry with respect to the x-axis. I'm going to abbreviate the phrase with respect to as WRT. That's a fairly common mathematics abbreviation because we use the phrase with respect to not infrequently. Do you have to use it? No. I'm just letting you know what it is and that I'm doing it, and that it's not uncommon. It's not just a Mr. Kulik abbreviation. That's a pretty common mathematics abbreviation. Yeah, with respect to. Yep. So let's just look at an example of something that's symmetric with respect to the x-axis. I'm just going to kind of sketch this in. So symmetry with respect to the x-axis means that if I take the half that's above the x-axis and I reflect it across the x-axis, it should lay right on top of the part of the graph that's below the x-axis. So really what this means is that, like, if I have the point AB, I also have to have the point A negative B. In general, what we're saying is that f of x has to equal negative f of x. Which is what we're seeing here, right? F of A equals B and F of A equals negative B. Is that okay with everybody? Okay. The next type of symmetry that we'll talk about is symmetry with respect to the y-axis. Sometimes, or frequently, we call this functions with this symmetry, we call them even functions. So again, just like when we said we have symmetry with respect to the y or to the x-axis, when we have symmetry with respect to the y-axis, if I take the stuff that's on the right-hand side of the y-axis and are reflected across, it should lie exactly on top of the other side of the graph. So what that's really saying is if I have the point AB, do a little bit, yeah, then I also have to have the point negative AB. Or more specifically, f of negative x has to equal f of x. Right? We have f of negative a is b, and f of a is b. Does that feel okay there? Okay. The third kind is called a 180-degree point. I'm abbreviating point with PT. Symmetry with respect to the origin. This is always the hardest one to draw, one that actually looks like it has that symmetry. So the idea here is if I have some point on the graph, if I think about this kind of like tying a rope to that point and then tying a rope to the origin, and then I rotate it like 180 degrees, you know, we have the same thing going on over here. So what we're saying here is if I have the point AB over here, I have the point negative A, negative B over there. We also sometimes call functions with this symmetry odd functions. Forgot to mention that. And in general, what we're saying is that f of negative x should equal negative f of x. Right? F of negative a is negative b, and f of a is b, but if I'm making that negative, I'd have negative b. Mackenzie?
Yeah, that's what I was saying. Like negative f.
You could write it that way also, although that's not the form that I would write it for the proof, but that's fine. That means that's an equivalent statement, right? If I divide both sides by -1, I have exactly what you're saying. So that's true also. That's an equivalent statement. Sure. Writing it this way will be more useful when we use it to prove things, because if I'm proving if something's odd or even, the way I've written it, both of them start with the same thing, so I can not know which one I'm looking for and just start with that and be able to just interpret what I get at the end, which is why we represent it that way as opposed to what you're describing. But that's not incorrect. Paul?
Can you explain the way you did it a little bit, Paul? Like the way you wrote it? Can you just kind of spell it out?
The f of negative x equals negative f of x. So f of negative a is negative b, right? F of a is b, but then we have a negative sign in front of it. So we just have negative b equals b, or negative b.
Oh, okay.
Right?
Yeah, it's the same thing.
Yeah, so this is just like, yeah, so like, cool? Okay, no problem. So what I'll ask you guys to do with this is to prove whether some functions are even, odd, or neither. We've got lots of time. So we'll do a couple of examples to kind of get us accustomed to this. So just to rehash, the tool that I'm using to do these algebraic proofs are these two facts. Right? Everybody's okay there? And now you see why it was useful to write it in this form, because both of them start the same way, so I don't have to figure out whether this thing, am I looking for something that's odd or something that's even. At looking at the equation, I'm not sure, but it doesn't matter to me because I'm going to start the same way, whether it's odd or even. You know what I mean?
Yep.
Okay, so we'll just start by doing f of negative x. So that's going to give me, when I do that, I'm going to replace all the x's in my equation with negative x's. Everybody's okay with that? A negative to the fourth power is positive, right? So negative x to the fourth just becomes positive x to the fourth, which is exactly what f of x is. So if I look at that string of equalities, I have f of negative x equals f of x, which just says that this is even. Does that feel okay there? Okay. Let's do a couple more. Okay, so g of x equals 2x cubed plus 3x. Again, we don't, on site, I don't know if this is going to be odd. Well, I mean, I do, and I can do it on site. But you guys don't know whether it's going to be odd or even yet. But that's okay, because again, to prove odd or even both situations, we're going to start the same way by figuring out what g of negative x is. So when I do g of negative x, I'm just going to plug negative x's in for all the x's in my function. If I have negative x to the third power, that is negative still, right? So that's going to be negative 2x cubed. And positive 3 times negative x is going to be negative 3x. I can see right away that's not exactly g of x, right? Because the signs are wrong. So I know it's not even. However, I notice that if I factor a negative sign out, that what I have left with is exactly g of x. So I have negative, because of the negative sign still out front, and then g of x. So I have shown that g of negative x equals g of x. So I can say that this is odd.
Okay, so it mirrors it exactly as even, and then if it doesn't.
If it's
you
its
don't get
opposite,
okay, opposite,
then it's odd.
And then you just don't get it close at all.
Yeah, so let's look at one more example where we get a neither. And then we'll ask some higher level question about what's going on, because there's actually some good observations that we can make here that make this, knowing what you're looking for, a lot easier. Like I'll show you how to do this basically on site. Now it doesn't get you out of doing the proof, but it tells you like, okay, on site I know that I'm looking, this is going to be odd. So if something doesn't quite work out, I know I've made like some silly arithmetic mistake and not that I'm proving something and gotten the wrong, like, oh, I made a mistake, so this must be neither. It's like, no, I know this is odd, so this needs to work. You know what I mean? All right, anyways. We'll start the same way. So h of negative x. Negative x squared is positive x squared, so I have 4x squared. Negative 3 times negative x is positive 3x. And then the 9 just stays plus 9. If I compare these two, well, I know this is not h of x, right? Because the signs aren't quite right. So I know then it's not even. Everybody agree with that? Okay, well, maybe if I factor a negative sign out, it'll work. If I factor a negative sign out, I have this. But after factoring a negative sign out, that's still not h of x. So I know I'm not odd. So that means it's going to be neither. Does that feel okay there? To see the neither is just one where the signs just don't work out. Okay. So let's see if we can detect a pattern going on here. So first observation, if I look at these three functions, f of x, g of x, and h of x, there's something in common to all three of them. What do you see that's in common to all three of them?
They all have a negative g of x, f of x.
I'm talking about the part in black. The original part. The original problem. This f of x, g of x, and h of x. What is in common to all three?
They all have exponents.
The exponents are different.
Okay, the exponents are different, and they all have exponents. I'm thinking of something a little bit more specific than that, though. What kind of function are all these? More general than quadratic. Polynomial. They're all three of these are polynomials, right? Okay. Now there's something about these polynomials that I can look at and tell whether they're going to be odd or even. So what property of the polynomial do you think we can look at? Yes. Okay. So what is what about the exponents is telling me that? Okay, whether the exponent is even or odd. But if I look at the first one, the exponent on 4 is even, but the exponent on 1 is odd. Well, it's not, you're close with the exponent, but it's not quite the exponent. What property of polynomials is related to the exponent, but not exactly the exponent? It's something we talked about a ton in Algebra 2. You probably conflated them as being the same thing when they're just a little bit different. Anybody remember? Degree, yes. So the degree of each term is not the same as the exponent. Often it is. The degree of x to the fourth is 4. But the degree of 1 is actually 0, because since it's a constant term, I can always tack on an x to the 0 at the end of it, right? So if I notice in the first one, the degree of x to the fourth is 4, and the degree of 1 is 0, what do you notice about both of those degrees? They're even, and this function was even. Okay, let's look at g of x. The degree of x of 2x cubed is 3, and the degree of 3x is 1. Both of those are odd, and the function was odd. And if I look at c, the degree of 4x squared is even. Okay, the degree of 3x is odd, and this function was neither. So what we would say is, at least initially, the sum of even degree monomials is an even function. And you could say the sum of odd degree monomials is an odd function. And this is great for polynomials, right? And this is true. Yes. The sum of even degree monomials is an even function. You know, is that, no, I guess that is pretty terrible looking.
What was A? You go over that one one more time.
Yeah.
Did you go over the first one? So I didn't get how you type down at 0.
Okay. So let's say we just have the number 4. 4 is the same as 4 times 1, right? And I know that anything to the 0 power is 1. Right? That was one of our properties of exponents. So I really have an x to the 0 at the end of any constant term, which tells me the degree, which is the sum of the exponents from the variables, for a constant term is 0. So this is a property of exponents, right? Since for any constant term, I can always think about it as that constant times 1, I can always have an x to the 0 at the end of any constant term, right? The definition of a degree is the sum of the exponents from the variable parts, which makes this a degree 0. We ignore the exponent on the 4 because it's not a variable.
Okay.
Is that cool?
Yeah, so if it, you go back up. Okay, so if it were, it says x to the 4th, if it were plus like x, then it wouldn't be, it would be neither, right?
Correct.
Okay.
Yeah, because you have an even and an odd degree.
Yeah, okay, that makes sense.
Okay.
Because it's just a number, then it would be an x.
Yes.
Okay.
Yep.
Okay.
Okay. So this what our observation here is great, provided that the function we're trying to determine whether it's odd or even is a polynomial. But could we be even more general? Could we say that the sum of even functions is an even function? Well, I don't know. Let's try to prove it. What do you guys say? So let's say we have f1 of x, f2 of x, yada, 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 to fn of x are even functions. And say that f of x equals then f1 of x plus f2 of x all the way down to fn of x. So this is just our setup. That's our statement, right? I've defined some even functions and then written a function that's the sum of even functions. Is that okay? So our proof then is we want to look at f of negative x. Well, composition tells me that I'll just replace my x's with negative x's in my function. Everybody good there? And since f1 of x is an even function, what does f1 of negative x equal? It's just f1 of x, right? f1 of x is an even function. That was one of our assumptions, that each of these was even. So f1 of negative x is just f1 of x, because that's the definition of an even function. And I can do that for each of these, since they were all even functions, right? And this is just f of x, so we're done. It's even. Whoa! That's pretty cool. The sum of odd functions will also be odd. The proof will be almost exactly the same, except you have to factor a negative sign at one point. Ooh, factoring a negative. But that's the big takeaway, is we kind of showed you now how to look at one of these, prove something is odd or even. And if you know if the if the parts of it, the terms are odd or even, you can tell on sight whether the function is going to be odd, even, or neither, without having to actually do the proof. Or, in the case of the homework where I'm asking you to do the proof, you know exactly what you're trying to prove. There's no guesswork as to I don't know, is this going to be odd or even? So you can't really get it wrong. You know what I mean?
Yeah.
Okay. I'm going to stop here. So your homework set, we're going to add in the problems. I asked you to do 1 through 12 last time. We're going to add in 13 to 22.
I kind of should stop there. Like, I was around.